In this video, we will talk about Fourier series, and Fourier series allow you to express complicated functions in terms of a trigonometric series. Sort of like a Taylor series allows you to express complicated functions as a series of polynomials, which is much easier to compute. So the Fourier series looks something like this. You have a starting coefficient, and then you have a sum of cosines with different frequencies and sines of different frequencies, and they have different coefficients in front of them. Each different frequency has a different coefficient. We will start kind of overviewing the Fourier series, and then we'll look at properties of sine and cosine. First, sines and cosines are periodic, which you probably know, but we do give a specific definition of what it is to be periodic with a period t greater than 0, and that is f of x plus t is equal to f of x for every value of x. So this is our formal definition of periodic. And the smallest value of t for which this f of x plus t equals f of x is true is called the fundamental period, because any multiple of t is also a period. But the smallest value is the fundamental period. The next property of sine and cosine we'll look at is linearity. So when f and g are two periodic functions with a common period t, then any linear combination at any product of f and g is also periodic with period t. And a linear combination of two functions is just a scalar multiple times the first function plus possibly a different scalar multiple times the second function added together. So this is the general form of the linear combination. And by scalar multiple, I mean any real number. So it's a real number times f plus a real number times g. We have a note that the period of sine m pi x over L and cosine m pi x over L is 2 times L divided by m. We can see this by noting that first, the period of sine and cosine are 2 pi, and the period of sine and cosine of ax is 2 pi over a. So if we choose a equal to m times pi over L, then we can see that the period of sine m pi times x over L, it looks nicer here how I wrote it out, or cosine m pi x over L is given by 2 pi times L over m pi, which reduces to the 2L over m, which is what we have over here. The other period of sine and cosine, which makes everything in our Fourier series works, is orthogonality. And we generalize the idea of orthogonality of vectors to orthogonality of functions. And we do that by generalizing the idea of the dot product, which is an example of an inner product. In particular, we'll generalize the idea of an inner product of two real valued functions. And by real valued, that means the results of these functions are real, not complex. So if we have u, which produces a real number, and v also produces a real number on the interval x a to b, then we're going to define the inner product to be the integral of a from a to b of u of x times v of x dx. And then functions u and v are said to be orthogonal if their inner product is equal to 0. A set of functions is said to be mutually orthogonal if each distinct pair of functions in the set is orthogonal. In other words, if you have a set of, say, 3 functions, if you take them pairwise, so any two of the functions is orthogonal, and it's true for all the pairs, then they're mutually orthogonal. And the functions of sine m pi x over L and cosine m pi x over L are a mutually orthogonal set of functions on the interval from minus L to L. As I mentioned, orthogonality is what makes this work and allows us to write any function, f of x, that's any function, as a sum of sines and cosines. And we can find these coefficients using these formulas here, which are the Euler-Fourier formulas. And for many of these integrals, integration by parts, which I have the formula for here, comes in handy. Last, I will comment in this class, Fourier series appear mainly as a means of solving certain problems in partial differential equations. However, Fourier series have a much wider application as tools to investigate periodic phenomena. A basic problem is to resolve an incoming signal to its harmonic components, which amounts to constructing its Fourier series representation, and then the magnitude of the coefficients determines the amplitude of each component. And you can see how this works. You have this incoming signal, and that's this f of x. It's just some sort of periodic waveform, not necessarily a particular sine or cosine, but just some signal that's coming in. And you want to kind of break it down to see what frequencies are in that signal, which makes up that signal. And here you have cosines and sines of different periods or different frequencies, and you weigh them with different coefficients, and you sum them together, and that gives you kind of a spectral analysis of this f of x. We'll start back at the beginning. The Fourier series allows you to express complicated functions in terms of trigonometric functions. And this is sort of like how the Taylor series allow you to express complicated functions as a series of polynomials. And here is our example of a series of trigonometric functions, cosines and sines. So we have a series of cosines and sines with different periods, different frequencies. We weigh them with different coefficients, and then we sum them together. And we do technically have this first coefficient, which is written out over here out of convenience, just for notation. We'll look at properties of sine and cosine, starting with periodic. So a function f is said to be periodic with period t greater than 0 if the domain of f contains x plus t whenever it contains x. And also if f of x plus t is equal to f of x for every value of x. The smallest possible value of t, which f of x plus t equals x for all x, is called the fundamental period. And a constant function is technically a periodic function with an arbitrary period, but no fundamental period. And here is an example. We have this waveform, and you can see it kind of repeats. And t is from the start of one waveform to the end of the other. And again, any multiple of t is also considered periodic, but the smallest t, for which this statement is true, f of x plus t equals f of x, is the fundamental period. So that would be this t here. And just taking a quick look at this definition, what we're saying is if we have an f of x, let's just pick one arbitrarily here. If we add t to this f of x, so t looks like it's what, 3 units? So what we will get is f of x plus t, so this y value is equal to this f of x. And that should be true for all values of x. The next property of sines and cosines is that they are linear. So if f and g are two periodic functions with common period t, then any linear combination, a real number times f plus another real number times g, and any product f times g is also periodic with period t. For the proof, we'll assume that f and g are periodic with period t, and then we will show that C1f plus C2g is also periodic. I'm not going to show this proof for you, but f times g is also periodic, but it's sort of similar. So we'll start with the definition of f and g are periodic. So f of x plus t equals f of x, and g of x plus t is equal to g of x. Then to show that C1 of f plus C2 of g is periodic, we want to show if h of x is equal to C1 f of x plus C2 g of x, we want to show that h of x plus t is equal to h of x. So I start with h of x plus t, and by definition, h of x plus t is equal to C1 f of x plus t plus C2 g of x plus t. Now because f is periodic, this means that f of x plus t is equal to f of x. Similarly, since g is periodic, g of x plus t is equal to g of x. And here, what I have is that this here is equal to h of x. So I have h of x plus t is equal to h of x, and I have shown that any linear combination f and g are also periodic. So for sine of mx over L and cosine mx over L, these are both periodic with fundamental period 2 times L over m. And we can see this since the period of sine and cosine is 2 pi, and the period of sine of ax and cosine of ax is 2 pi over a. If we choose a equal to m times pi over L, then the period t of sine of m pi times x over L and cosine m pi x over L is given by t is equal to 2 pi L over m times pi, which is 2L over m. The other note I have is since every positive integral multiple of a period is also a period, each of the functions m times pi times x of L and m times pi times x over L has common period 2L. The last property we will look at is orthogonality of sine and cosine. So to generalize the idea of orthogonality of vectors to orthogonality of functions, we're going to start by generalizing the idea of the dot or inner product of vectors to an inner product of functions. So the inner product of two real-valued functions u and v on the interval will be defined as the integral from a to b u of x, v of x dx. So you might remember inner products from vector calculus, and we defined the inner product on two vectors as the dot product. And these were the important properties of the dot product, which is the important properties of the inner product. So now that we have this integral as our definition of the dot or inner product of two functions u and v, we can see that this inner product definition of two functions satisfy the same four properties of an inner product. And by the way, I only wrote the first part of each property. I didn't do the second part, just because it's not so much that I want to go through this or explain this a lot, but if you remember this from vector calculus, then it's totally analogous. It's an inner product defined for functions. And the other thing you might remember is functions were said to be orthogonal if their inner product is 0. So for two functions to be orthogonal, their integral, when you multiply them together and integrate, is equal to 0. And again, that's exactly analogous to our inner product of vectors. If you remember, a dot b was equal to the magnitude of a, magnitude of b times cosine of theta, which meant a dot b is equal to 0 if and only if a and b were orthogonal or at a 90-degree angle. So it's the same idea. So in linear algebra, if you've had that, we abstracted the notion of a vector, and we can say that u and v are part of a vector space of functions, and we use the inner product, which was defined as this integral, to abstract the notion of orthogonal. So two functions are orthogonal when their inner product is equal to 0. If you don't remember this stuff from vector calculus or you haven't had linear algebra, don't worry about it. This is the important thing. This is how we define the inner product, and we define orthogonality as when the inner product is equal to 0. A set of functions is said to be mutually orthogonal if each distinct pair of functions in the set is orthogonal. So for example, if we have three functions, u of x, v of x, w of x, we would say they are mutually orthogonal if the integral ux vx dx is equal to 0, ux wx dx is equal to 0, and vx wx dx is equal to 0. In other words, any two pairs will be orthogonal. And then last, the functions sine of m pi x over L and cosine of m pi x over L, for m is equal to 1, 2, up to infinity, so all the natural numbers, form a mutually orthogonal set of functions on the interval x from minus L to L. So in other words, when we go from minus L to L, cosine of m pi x over L times cosine of n pi x over L dx. So if m and n are not equal, they are orthogonal. So the integral is 0, right? Here it says the functions form a mutually orthogonal set. So if they have different periods, then they are orthogonal. If they have the same period, then this integral works out to be L, equal to L. Similarly for sine, if you have sines of different periods, when you take this integral, they are going to be 0. They're going to be orthogonal. And if m and n are equal, then this integral, the inner product, will be equal to L. Last, if you take a sine and cosine, and they can actually have the same period or different periods, so for all m and n, this inner product will equal to 0. So in other words, cosines and sine functions with different periods will be mutually orthogonal. The proof of each of these three is actually quite short, and I will do the proof for the first one. And the proofs all use these trigonometric identities here. So here I have two cosines with different periods, so I'll be using this trigonometric identity. So this integral of cosine m pi x over L times cosine n pi x over L will be equal to, here I subtract and then I add. So cosine of m minus n pi x over L plus, and this is where I add cosine plus m pi x over L dx. We can then integrate and we'll get this 1 over m minus n sine of m minus n pi x over L and 1 plus m plus n sine of m plus n pi x over L. When we plug in an L, you can see that the L's disappear, and then we have a sign of some integer, since m and n are integers, times pi, right? Plugging in L for x. So this here goes to 0. Similarly here, when we plug in L for x, we're going to have an integer times pi. So the sign of some integer times pi, this also goes to 0. So this whole integral here is equal to 0. And a critical thing to note here is that because we have this division, m minus n cannot equal to 0. In other words, and also we want m plus n not equal to 0. So in other words, m does not equal n. So when m does not equal to n, which is exactly what we have here, the integral equals 0. As I mentioned, these other two proofs are very similar. They just use the other two trigonometric identities. I do need to talk about what happens when m equals n. So if m equals n, then our integral becomes cosine m pi x over L squared dx. And now I just need to use these half-angle formulas, and I can integrate, and I get L. So now if our goal is to express this function f of x in terms of a summation of a bunch of sines and cosines plus some constant out in front, we can use the fact that sine and cosines are orthogonal to find the coefficients a sub m. So in particular, the two steps we're going to do is multiply by cosine of n pi of x, where n is fixed, and then we're going to integrate. So to multiply the this is the left-hand side of our equation here by cosine n pi x over L, and then integrating, we're going to get the integral of f of x times cosine n pi x over L. And then that's going to equal to, and we're going to do the same thing to the right-hand side. We're going to multiply everything by cosine n pi x over L, and then integrate. So first, let's just look at this constant term. It gets multiplied by, so our 1/2 a naught gets multiplied by cosine n pi x over L, and then we integrate. And when we integrate, we can just pull out the constant. This next term here, we're going to multiply am, it's going to be pulled out of the integral, times cosine of m pi x over L times cosine n pi x over L. So that's this part of our series. And then we also have to do the same for this last part of the right-hand side of the equation, the bm sine n pi x over L. It gets multiplied by cosine n pi x over L. So here's our sine n pi x over L times cosine n pi x over L. This b of m comes outside of the integration. So here we have the left-hand side of our equation, and on the right-hand side, when we have sine times cosine, those all go away. Here, they all go away except when m is equal to n. So what we're left with is our an, so we just called it n, we could have called it m, but an, the integral cosine squared of n pi x over L dx. And so this here, remember, when we have the same, when m equals n, this integral is equal to L. So now we have the left-hand side is equal to a and L, which means a sub n is 1 over L. The left-hand side, this integral here, integral minus L to L, f of x cosine n pi x over L dx. We do something similar to find b of m. We multiply both sides of the equation by sine of n pi x over L, and then we integrate, and we get b of n is equal to a similar expression, this equation here. And these two equations for a sub n and b of n are the Euler-Fourier formulas. So I've written the formulas we have derived here, and now we can do some examples. The first example is a periodic triangle wave, and here's the function. F of x is equal to negative x when x goes between negative 2 and 0, and f of x is equal to x when x goes between 0 and 2. We can see that our period is equal to 4. If our period is equal to 4, L is equal to 2, so our f of x by our formula here is 1/2 a naught, the sum from m equals 0 to infinity, am cosine, and now L is equal to 2, m pi x over 2 plus bn sine of m pi x over 2. So when m is equal to 0, we can get a naught. So a naught is equal to, using our formula here for a sub n, 1/2, remember L is equal to 2, 1/2 integral from negative 2 to 0, because we have to put in this formula, minus x cosine, and now m is equal to 0, so we're going to put cosine of 0 dx plus 1/2, and now we'll put in this part of the formula from 0 to 2 x cosine of 0 dx, and integrating this becomes 1, and integrating gives us a naught is equal to 2. Now for m greater than 0, we have our formula a sub m is equal to 1/2 from 0 to 2, our f of x, negative x, cosine of mx pi over 2 dx, plus 1/2, and then our other part of our formula, 0 to 2 x, cosine of m pi x over 2 dx. And we're going to integrate this using our integration by parts. Because the integrals are a little bit long, they're not terribly long, but a little bit long, I'm going to separate my work. So first I'm going to do this half of the sum, and then later I'll do the second half. So for integration by parts, if you look at this formula, our v and v prime don't necessarily need to change much, but our u can be reduced to u prime. So this argues for u being equal to negative x because u prime can be reduced to negative 1, whereas our v prime will equal to cosine m pi x over 2. So v is 2 over m pi sine of m pi x over 2. We plug in to our integration by parts formula, so we have u times v. Where's u? So I have my minus x times v minus the integral of v times u prime. So u prime is minus, so that's going to become a plus, and our v is over here. So this we can integrate, and you see that I've done the integration, and then I can plug in my 0 and negative 2. And you can see when I plug in 0, sine of 0 is, well, actually 0 here also, the x is 0, so this will go away. And when I plug in negative 2 over here, you can see that I'm going to have sine of some integer times pi. So this is also going to go away for both values. So what I'm left with is my 2 over m pi squared cosine m pi x over 2. I plug in 0. This becomes 1. I plug in negative 2 here. I get my minus m over pi. So what I have is minus 2m pi squared, since this is 1. And then I am left with, because cosine is an even function, this is simply equal to cosine of m pi. Second half of the sum is very similar. It's just that instead of this negative x for f of x, I have a positive f of x. So I'll leave it to you to do this integration by parts, and this should be the solution you come up with. Plugging in the two results I have from my two integrals into this equation here now, I have am is equal to 1/2. I plug in the results for my first integration, and then the results for my second integration. I can see that it simplifies some. I can combine my cosine of m pi terms, and I can combine my constants, and I get a final answer of a to the m is equal to 4 over m pi squared cosine of m pi minus 1. So just to recap what we have our general form of f of x here. We solved for m equals 0, and we found that a naught was equal to 2. When we solved for m greater than 0, we found that a of m is equal to 4 over m pi squared cosine of m pi minus 1. And we see when m is odd, this here gives us cosine of a negative pi will give us a negative 1, so our answer will be negative 8 over m pi squared. Whereas when m is even, cosine is going to be equal to 1, and so here we'll have 0, so our am is equal to 0. So now we have a solution for our am and a naught. And now we need to work on our b sub m. So for b sub m, we're only looking at m greater than 0. A naught only occurs once. It's out here, but it occurs with our even functions with cosine. So here we have m greater than 0. bm is equal to our 1 over L, which is 1/2, integral from negative 2 to 0, our f of x, and now we multiply by sine of m pi x over 2 dx, plus, and the other half of our integral, 1 over 2, 0 to 2, and now we have x times sine of m pi x over 2. Very similar to what we did last time, we're going to use integration by parts, and I'm also going to integrate this half of the sum first. So I choose my negative x to be u, and my sine of m pi x over 2 to be v prime. So I have u prime is equal to negative 1, and v is equal to 2 over m pi times cosine m pi x over 2. So looking at this here, I did both sides of the integral first. So I did my 1/2, and then I have my u times v. So I have my minus x, so I put my minus with my 2m pi. So I have my x and my v, and I need to evaluate that between 0 and negative 2. And then my minus, my v times u prime. Since u prime is a minus, I have a plus. My integral from negative 2 to 0. My v times u prime, I've already got my u prime, so v is 2 over m pi cosine of m pi x over 2. And then I also did this equation here, very similar. I'll let you take a look. I carried this down, and then I did this integral. So I'm going to have my 2m pi squared, and then sine of m pi x over 2 evaluated at 0 and negative 2. Similarly here, I carried this down, and I did my integral so that I have my cosine going to sine. When I plug in 0 for my x, I get 0. When I plug in negative 2, I get positive 4, but this is, the first term plugged in minus the second term plugged in, so I still have my minus. So I have my 4m pi, and then cosine, when I plug in my negative 2, they cancel, except I'm left with a negative m pi. Similarly here, when I plug in my 0 into sine of 0, I get a 0. When I plug in sine of negative 2, I'm going to get a sine of negative m pi. And then I'll let you take a look at this half of the equation. And then you can see I simplified here a couple of things I did. Since cosine is an even function, I just dropped the negative here. Since sine is an odd function, I took out the negative, but I had to change my sign over here, multiplied by another negative. And here I have my cosine, I have my sine, and what you can see is this will cancel with this term, this sine term cancels with this sine term. And so what I'm left with is my b sub m. All my sine coefficients will be equal to 0. Adding that to our other coefficients, our a naught is equal to 2, our a sub m is equal to this function, and our b sub m is equal to 0. So I took this equation and I moved it down over here so I can write my final answer. I have my 1/2 a naught. My a naught is equal to 2. And now all of my b sub m, they go away. So this, I'm not going to have any sine terms, only cosine terms. So when m is equal to 1, because I'm going to sum from m equals 1 to infinity. So when m is equal to 1, I have my minus 8 over pi squared times my cosine, m is equal to 1, so that's pi x over 2. When m is equal to 2, I have a 0 term because m is even. So when m is equal to 3, I'm going to have my minus 8/9 pi squared times cosine of 3 pi over 2x. And it continues. I can leave my answer in this form, but I did a little bit of algebraic manipulation just to get back another summation form. And so this is my equation that represents this triangle wave, which is kind of impressive if you think about it, because this triangle wave, I mean, other than it being periodic, doesn't really look like a sine or cosine. Well, in particular, we're modeling it with cosine. Doesn't look like a cosine function. But you can try it out. In other words, of course, you're not going to go from n equals 1 to infinity, but even if you tried n equals 1 to 5 and you plug this in, you'll see that the cosines, when you add them together, they quickly start to look like a triangle wave, which is kind of amazing. And in particular, we can ask, how quickly does this series converge? In other words, determine how many terms are needed so the error is no greater than 0.01 for all x. In other words, approximating this triangle wave with this sequence here of cosines, well, 1 minus the sequence of cosines. And just to give you an example of what this looks like, so the mth partial sum is s sub m, 1 minus our 8 over pi squared, and now instead of n equals 1 to infinity, we can go from n equals 1 to m. So if I wanted to calculate S3, I would have 1 minus, and then m equals 1. So I have my 8 pi squared. My 1 plugged into here would give me 1 squared times cosine of pi over 2x. When I plug in 2, I get 4 minus 1 is 9 squared, so 1/9 cosine of 3 pi over 2x plus, let's see, that was 1, 2, when I plug in 3, I get 5 squared, so 1 over 25 cosine of 5 pi over 2x. So this is S3, my third partial sum, and you can graph this and see what it looks like. And so a couple of things. First, the coefficients diminish. You can see that they kind of start to get smaller as this coefficient here, 1 over 2 pi minus 1 squared, diminishes. So this converges fairly rapidly, kind of with the squared, and when things are inverse squared, they diminish rapidly. So let's consider the error, which we designate with em of x, which is equal to f of x minus the partial sum of m. So I have this graph for E6, for when we let m equal 6 versus x. And what you can see is for this graph, the errors peak at x equals 0 or 2, and in particular, it peaks somewhere around 0.03, in particular 0.034. It's less than 0.034 for x between 0 and 2. So the other thing I know, since the error peaks between 0 and 2, I can look at em of 2. So I'm going to pick this x value of 2, I'm going to calculate the error for m equals 2, 4, 6, 10, 15, 20, and 25. I put this in a spreadsheet. And what I got were these numbers here. So if I want an error no greater than 0.01, I need to choose some number between 20 and 25. And this type of analysis is not something you're going to do by hand. You'll plug it in to some nice graphing or calculating sort of thing. I actually just used a spreadsheet. For our next example, we're going to look at f of x is equal to 0 between -3 and -1, 1 between -1 and 1, and 0 between 1 and 3. So these two areas make our integration really easy. So you can see then our period is equal to 6, which means L is equal to 3, and the problem is to find the coefficients in the Fourier series. And actually it also said to graph. So here is the graph, right? We're at between -3 and -1, we're at 0, and then between -1 and 1, we're at 1, and then we drop back down to 0 up until 3. And since this is periodic, I just kind of repeated the pattern. And you want to note that even though f of x is not assigned a value at the points of discontinuity over here, such as x equals -1 and 1, this has no effect on the Fourier coefficients, since the value of an integral is not affected by a single point, or even a finite number of single points. So I've written t, our period is 6, and L is equal to 3. So now to do a naught, m is equal to 0, or here I guess it's designated as n, and we have the 1 over L, 1/3, from minus L to L. So our first interval is from -3 to 1, but we're integrating 0, so this is going to go away. Our next interval is from -1 to 1, and then we have f of x is equal to 1, and then cosine, and when we plug in our m equals 0, or in this case n equals 0, we get cosine of 0 is equal to 1, and our next interval is from 1 to 3, but we're integrating 0, so this goes away, and what we're left with is just integrating 1 from -1 to 1 multiplied by 1/3, so we get 2/3 for a naught. For m greater than 0, a sub m, again we have our 1 over L, 1/3, from -3 to 1, again this goes away because f of x is 0. Also the 1 to 3, that'll go away because f of x is equal to 0, 1 to 3. So we're really only concerned about -1 to 1. And then we have f of x, which is 1, cosine of m pi x over L, which is 3. When we integrate, we carry our 1/3, we have our 3 over m pi times sine of cosine m pi x over 3, evaluated at 1 and -1. When I plug in my 1, I get my sine of m pi over 3. Plug in -1, I have my sine of negative m pi over 3, but because sine is an odd function, then this becomes negative, and with this negative it becomes positive, sine of m pi over 3. So we have the 2 times sine of m pi over 3, also divided by m pi. Doing something similar for b of m, and again, our integral from -3 to 1 and our integral from 1 to 3 has the 0, so those are going to go away. So we just need to integrate from -1 to 1, our f of x, which is 1, sine of m pi, right, now we're doing the sine, m pi x over 3. So that gives us cosine of m pi x over 3. And when you plug in the 1 and you plug in the -1, you're going to get 0. So now I have moved my formula here for my Fourier series, and I have a naught. We have shown that that was 2/3. We showed our am is equal to 2 m pi sine of m pi over 3, and we showed that b of m are all equal to 0. So plugging these things into my f of x, I have my 1/2 a naught, so that will give me 1/3, plus the sum from m equal 1 to infinity. Now I'm going to have my am, which is equal to 2 over m pi sine of m pi over 3, times my cosine of mx over 3, m pi x over 3, and all my bm are zeros. And this form of the answer is just fine, but I did write out a few terms just so I could kind of get a feeling of what it looks like. For our last example, we're going to look at the function 1/2 x squared, x between -2 and 2, and f of x plus 4 is equal to f of x. We are going to find the Fourier series. We're going to sketch the graph, find the Fourier series, plot the partial sum, Sm, of x versus x, and then for m equals 5, 10, and 20, and then we're going to describe how the Fourier series seems to be converging. So the first thing is to plot. So between -2 and 2, I have my 1/2 x squared, so I have my parabola, and then it's periodic with period t is equal to 4. So right between -2 and 2 is 4, so I just kind of move this whole graph over, and it keeps kind of repeating. To find the Fourier series, I'm going to start with m equals 0 to plug into my formula an here, and I have 1 over L. Well, since t is equal to 4, L is equal to 2, so that's 1/2, and I'm going to integrate from -2 to 2 of f of x, 1/2 x squared, times cosine n pi of x. And now because m, or n in this notation, is equal to 0, that just becomes cosine of 0. So once I integrate, what I get is a naught is equal to 4/3. For m greater than 0, I'm going to look at am is equal to 1 over L, that's our 1/2, and then our f of x. So I went ahead and moved this 1/2 out here, so then I have my x squared times my cosine m pi x over 2, and we're integrating from -2 to 2. For this integral, I'm going to use integration by parts, and I'm going to let u equal to x squared because u prime will then simplify to 2x, whereas this cosine is just going to keep going back and forth between sine and cosine. It doesn't really simplify when you take the derivative. So that's why I chose the cosine as my v prime, and then my v is 2 over m pi sine of m pi x over 2. Using my formula for integration by parts, then my integral is equal to u times v, which is x squared times my 2 m pi sine of m pi x over 2. So comparing that over here, I have my 1/4, that's just this 1/2 times 1/2. And then my u times v, I have my 2m pi, I have my x squared u, and then my sine of m pi x over 2. And I need to evaluate that between -2 and 2. But the rest of my integral is equal to minus the integral of v times u prime. So I'm taking out my 2, and then I have my x, and then times v. So here's v. I have my sine m pi x over 2 dx. So I kind of simplified my 2 with my 4. I get 1 over 2 m pi. Over here, I have my x squared, so that's 2. And then I have my sine of m pi, and the 2 here cancels with the 2 below, so I have sine of m pi. And then I have minus, plugging in the -2, I still get my positive 4. And then I have my -2 canceling with the 2 on bottom, but I have a minus m pi. Over here for the integral, to make progress with this, I have to use integration by parts one more time. I'm going to let u equal to x, u prime equals 1. Again, u is being simplified when we do this integration by parts, whereas our v prime, it just kind of goes back and forth. These two terms, these two signs of m pi, I combined. Remember, sine is an odd function, so I just need to add this. This becomes a positive, and this is 4 sine of positive m pi. So this will give me 4 plus 4, so that'll be 8 sine of m pi, but I'm dividing by 2, so that becomes 4 over m pi sine of m pi. So this here reduces to this. And now I have this integral, which I need to do by parts. So first I simplified these 2's, and I have 1 over m pi. And then I have, by my formula, u times v. So I have x times v. So I have my 2 m pi, my x, and then my cosine m pi x over 2, evaluated at -2 and 2. And then the rest of my integration by parts formula, v times u prime. So the integral of v times u prime, which is just 1. So I'm going to pull this out. With the negative and this negative, I'm going to get a positive. So I have a 2 m pi integral from -2 to 2 cosine of m pi x over 2. So the first thing I can simplify right away, since m is an integer, is the sine of m pi. So both of these go, you know what, it goes away here, and I actually carried it down over here before I realized I could cancel it out, but this goes away. Now here, I multiplied the outside by -2, so I get a positive 2 over m squared pi squared. I have my x, which is equal, when I plug in my 2, this becomes 2 cosine of m pi, since the 2 cancels with the 2 on bottom. And then I'm going to subtract, and I'm going to put my -2 here, and my -2 with the subtraction gives me a plus, and then I'll have a cosine m pi negative. The -2 and the 2 cancel, but I'm left with the negative. But since cosine is an even function, it's equal to cosine of m pi. So that's this part here is this term here. And then last, I have the same sort of thing. Cosine integrates to sine m pi x over 2, and I multiply by a factor of 2 over m pi. And then I evaluate at 2 and 0. But again, because of the 2, this cancels out, and I get these cancel out, so I get sine of m times pi, where m is an integer, so that goes to 0. Similarly, with the -2, this will go to 0. And what I'm left with is just this middle term here. So I have 2 cosine m pi plus 2 cosine m pi, that's 4 cosine m pi times 2, that'll be 8 m squared pi squared cosine of m pi. And so I've kind of rewritten it over here. 8 over m squared pi squared cosine of m pi. That is our a to the m term here. And so I've written that here. So far we have a naught is equal to 4/3, and am is equal to 8 to the -1m over m squared pi squared. Now we can look at bm. So it's 1 over L. L is equal to 2, so 1/2 f of x, which is 1/2 x squared, so I took out my 1/2 already. And then I have the integral from -L to L, and as I said, I already have my x squared, and then sine of m pi x over L, which is 2. But since sine is an odd function, when we integrate from -L to L, we're going to have this whole integral is going to be equal to 0. So bm is equal to 0. And now I can plug everything into my formula here for my function f of x, which is 1/2 x squared, we're approximating that function, is equal to 1/2 a naught, which is 2/3, plus, and now we're going to sum our am times cosine m pi x over L. So here's our am, and we're going to multiply it times cosine m pi x over L. So here I have cosine, now I use my index of n, so I have cosine n pi x over L, and L is equal to 2. And then what happened to our am? So m should be inside the summation, but the a pi squared I can pull outside the summation. And now I have my -1 to the n over n squared. So this is our estimate for our f of x, which again is 1/2 x squared. So this example is kind of nice because it gets to how quickly our series here can approximate our function 1/2 x squared. So our f of x from our previous work is equal to 2/3 plus 8 over pi squared, sum from n equals 1 to infinity, minus 1 to the n over n squared cosine of n pi over 2x. And of course, we can't sum to infinity, but we could take partial sums. That's what these s of m are, partial sums. So our partial sum is essentially the same formula, but instead of going from n equals 1 to infinity, for the mth partial sum, this m here, we're going to go from n equals 1 to m. So for example, s of 5 is for n goes from 1 to 5. So we have our 2/3, and then when we plug in 1 for m, we get a over pi squared times, plugging in 1, this becomes -1 over 1, so that's a minus, cosine of pi over 2, x, plus plugging in n equals 2, so now we have a positive 1 over 4, so that's our 1/4, times plugging in 2 for I get cosine of pi x. For n equals 3, I get a negative over 9 times cosine of 3 pi over 2x. For n equals 4, I get a positive 1 over 16 cosine of now 2 pi x. And then n equals 5, I get minus 1 over 25 cosine of 5 pi over 2x. Now I can plot this. So in black, I have my original f of x is equal to 1/2 x squared. In blue, I have my m equals 5, this partial sum plotted. And you can see it's following fairly well, but you can see kind of the signs of you can see the remnants of the cosine function. It still looks sort of like sine cosine. By the time you get to m equals 10, however, and so this is something you would do on a computer to plot. By the time you get to m equals 10, you can see that it's getting to look more and more like the peaks. And then by m equals 15, you almost have an exact fit. So it actually converges pretty quickly, 15 terms, and you're pretty much using your sines and cosines to totally accurately estimate 1/2 x squared. And the terms diminish as 1 over n squared diminishes, and you can just see that from here, that our coefficients start to get smaller with the square. So it converges fairly rapidly, which you can also see in the graphs below, which is really quite remarkable, because to think that you can take any periodic function and estimate it by using a bunch of sines and cosines. So to review what we looked at the Fourier series, which we wanted to represent a complicated function in terms of a trigonometric series. And so this is the form we were after, the a0 over 2, some constant, plus the sum from m equals 1 to infinity, a coefficient times cosine of m pi x over L, plus a coefficient times sine m pi x over L. So a linear combination of sines and cosines. Our properties of sines and cosines, first we found that it was periodic, as you know. Our period was called t, and the formal definition of being periodic is that f of x plus t is equal to f of x for every value of x. And the smallest value of t, which this is true for, is called the fundamental period. And we need to distinguish that because any multiple of t is also a period. The second property we have of periodic functions is that they are linear. So if f and g are two periodic functions with a common period t, then any linear combination of f and g, that is, if you multiply f by some real number and you multiply g by some real number and then add them together, that would be a linear combination. And any product f times g is also periodic with period t. And we noted that sine of m pi x over L and cosine of m pi x over L are periodic with fundamental period 2 times L over m, and we kind of had some notes on how to derive this fact. The last property we have of sine and cosine is orthogonality, and this ended up being a very important property. And what we did to get the idea of orthogonality of functions is we generalized from the idea of orthogonality from vectors. And the way we defined when vectors were orthogonal is we talked about the inner product equal to 0. So for two functions that produce a real value, we define the inner product to be the integral of u times v. So the inner product of function u and v is the integral from a to b, u of x, v of x times d of x. Then the functions u and v are said to be orthogonal on a and b if their inner product is equal to 0. And then a set of functions is said to be mutually orthogonal if each of the distinct pairs of functions in the set is orthogonal. And it turns out that sines and cosines form a mutually orthogonal set of functions on the interval minus L to L. And we use this orthogonality to help us find these coefficients when we want to write f of x in terms of sines and cosines. And what we got were these two formulas, the Euler-Fourier formulas to find a sub n coefficients, the coefficients in front of cosine, which is 1 over L, integral from negative L to L, f of x cosine of n pi of x over L dx, and then b of n would be 1 over L, integral from minus L to L, f of x sine of n pi x over L dx. And again, we used orthogonality and the integral in order to find these formulas. So in this class, and also because this involves a lot of integrals, we often used this integration by parts formula. So in this class, Fourier series appear mainly as a means of solving certain problems in partial differential equations. However, Fourier series have a much wider applications as tools to investigate periodic phenomena. And a basic problem is to resolve an incoming signal into its harmonic components, which amounts to constructing its Fourier series representation, and then the magnitude of the coefficients, these a sub m and b sub m, determines the amplitude of each component, each cosine and sine component. So that's it for this video. Thank you for watching.